In this lesson, we want to write a program to control the level of the liquid in this tank. The facilities that we're going to use for this task are these two liquid level switches and these two valves. Now, let's define the conditions of our program. We need to write the program in such a way that when the level of the liquid drops to the set minimum while this discharge valve is closed, the inlet valve opens up to fill the tank. When the tank is filled up to the maximum set level, the inlet valve will close and the discharge valve will open to drain the tank. So our program has two modes, a filling mode and a drain mode. In the filling mode, the inlet valve is open and the discharge valve is closed. In the drain mode, the inlet valve is closed and the discharge valve is open. In reality, having the valves open and close repeatedly to fill and drain the tank in a continuous cycle is not a practical operation, but that's not important in this scenario, as the goal here is to improve your programming skills by using various examples. Okay, so in order to start programming after creating a new project and configuring the hardware, we open the OB1. To make writing and analyzing the program easier, we first need to create some symbolic names for the absolute addresses. So to do this, we open the symbol table from the option menu. As you can see, we have two level switches that are connected to the PLC input module and two valves that are connected to the PLC output module. Assuming that the low-level switch is connected to the first channel of the digital input module, its address will be IOO. So in the table, we type low level in the symbol section, and in the address section, we enter IOO, then hit enter. As we have discussed in earlier lessons, because all the inputs and outputs are digital throughout this course, the data type for all of them is left as Boolean. For the next level switch, we enter high level as a symbol, and assuming that it has been connected to the second channel of the DI module, its address will be IO1. For this valve on the top, we assign the symbolic name of inlet valve, and as it's connected to the first output of the PLC output module, we enter the address Q40. For the down valve, we use the name discharge valve and enter Q41 for its address as it's connected to the second output. Finally, we save this table and navigate back to the OB1. Okay, to fill the tank, we want the inlet valve to be energized and to open when the liquid drops down to the minimum set level. So we can insert an SR flip-flop here and then add an open contact in the set input, assigning it to the address of the low-level switch. At the output of this flip-flop, we are going to add a coil, assigning to it the address of the inlet valve. With these settings, when the low-level switch is energized, the output will be turned on. Now, how long does it stay turned on? Well, as we said earlier, the valve should stay open until the liquid reaches the maximum set level. Okay, now which one of the facilities is able to detect the point at which the liquid reaches the maximum level? Yes, you're right, the high-level switch. So we can assign the address of the high-level switch to the reset input so that when the liquid reaches the maximum level, it turns off the output and closes the valve. We also need to enter a memory bit address for the flip-flop here. We can enter an address like MOO, or we could also enter the same address that we assigned to the output. Okay, this network works for the fill mode, but what's going to happen when the tank is filled up? Well, as we said earlier, after the tank is filled, the inlet valve should close, and the outlet valve should open. So, we're going to add a new network here, and then insert an SR flip-flop here. We need the discharge valve to open when the high-level switch is energized, so we need to insert an open contact here and assign it to the address of the switch. Then we should insert a coil in the output and assign it to the address of the discharge valve. To close the valve until the liquid drops down to the minimum level, we can assign the address of the low-level switch to the reset input. And we enter Q41 here as a flip-flop memory. Okay, the program looks to be complete now, so we're going to save it and then go to the Symbolic to download the OB1 to the CPU. We put the program into monitor mode in the OB1 and begin testing the program. As you can see, at the start of the operation, none of the switches is energized, so none of the outputs are energized either. But as soon as we energize the low-level switch here, the set input is energized, triggering the output and opening the inlet valve. With this valve open, the tank starts to fill up. Now, if the liquid rises past the level of the low-level switch, it stops being energized. But as you can see, since we have used a flip-flop here, the output remains true in these conditions. So, how long will the output remain true? Well, the valve remains open until the liquid rises to the maximum level and energizes the high-level switch. So now, we energize this switch, and you can see that it works as expected. The machine is now in drain mode. This cycle of filling and draining repeats as long as the PLC is in run mode. This is another practical example of using flip-flops.